Imagine the beginning of everything, a time when the universe was just setting the stage for the grand play of cosmic history. A simple gas cloud contracting, struggling against the vast emptiness of space and giving birth, not to a living creature, but to a star. This celestial body, more massive than 95% of all the stars in the universe, would be the cradle of a potential rocky world, teeming with life and... Wait for it. Yes, you guessed it, that star is our sun. And the life? That's us. But wait, it gets even more remarkable. The most fascinating part of this cosmic tale. You'll have to stick around to find out. What's up, my amazing and curious folks? Ready to unravel mysteries together? I'm your host, Caesar, and with me is the vivacious and insightful Sonia. Are you ready, Sonia?
Hi, everyone. I can't wait to dive into today's topic with Caesar.
Awesome, Sonia. And remember, folks, to subscribe to our channel and hit the bell icon to keep up with us on Curiosity Wonderland, where we unlock the secrets of the universe every day at 10, 14, and 20 hours. Let's get started. So the tale of our sun's birth begins when the universe was just 2/3 of its current age. Picture a time when hundreds of billions of stars were already shining in our galaxy, the Milky Way, and gas clumps were occasionally contracting along its spiral arms to trigger star formation.
So, in a sense, our galaxy was like a star factory, constantly producing new stars?
Exactly. And within one of these star-producing regions, about 9.2 billion years after the Big Bang, a cloud of gas collapsed, giving rise to many new stars and likely a star cluster. One of these stars was our sun.
And this process, it's been happening almost since the beginning of the universe?
Yes, almost. Since about 50 to 100 million years after its inception, the universe has been constantly giving birth to stars. Gas clouds contract, undergo a process known as core fragmentation, and then stars are born.
But our solar system, with its rocky planets and conditions for life, that was something special, wasn't it?
Indeed. For a stellar system like ours to develop with the right ingredients for life and conditions suitable for habitation, it took a considerable amount of time and cosmic evolution. So, while our sun is one among countless stars, its story is indeed quite exceptional. Our sun's journey to existence wasn't a simple process. It took several generations of stars living, dying, going supernova, and having stellar remnant collisions to fill our galaxy with the heavy elements necessary for the creation of rocky planets and life.
So basically we're made from star stuff?
Absolutely. You could say we are all stardust, but it gets even more interesting. A star needs to possess at least 8 to 25% of the sun's heavy elements to form rocky planets.
That's quite specific.
Yes, it's a delicate balance. And our solar system was situated just right, about 27,000 light-years from the center of the galaxy, in an area dense with the heavier elements, conducive to the formation of a rocky planet like Earth.
So our solar system won the cosmic lottery, in a sense.
You could say that. And consider this. When our solar system first formed, it was made up of about 70% hydrogen and 28% helium, with just about 2% of everything else combined.
It's remarkable to think about the journey that led to our existence, isn't it?
Absolutely. It's a testament to the beauty and complexity of our universe. Now, the way most stars form in galaxies like ours is quite a spectacle. Imagine clouds of gas in the disk of our galaxy sweeping through one of the spiral arms. As they do, material gets drawn into these clouds, and density waves ripple through the galactic disk, causing the gas and dust to bunch up, achieve an even greater density than before.
So this is like a massive cosmic traffic jam?
That's one way to put it. When the traffic jam gets intense enough and the gas and dust can cool themselves quickly by radiating heat away, gravitational collapse becomes inevitable.
And that's when star formation kicks in?
Exactly. These gas clouds, which can range from thousands to millions of times the mass of the sun, start to fragment into tiny clumps. It's quite a race, with gravity working to form and grow stars, and radiation from the hottest stars trying to evaporate that star-forming material away.
It's a cosmic battle, then, between creation and destruction. Quite poetic, isn't it?
Indeed. The universe operates on scales and processes that are as epic as any poetry. As time goes on, it becomes apparent who the real winners are in this galactic game. You might assume it's the most massive stars, the ones that are tens or even hundreds of times as massive as our sun. They emit radiation thousands to millions of times as luminous as our own star. And in terms of mass, temperature, brightness, and overall emitted energy, these are the grand winners.
The bright stars of the cosmos.
Precisely. But here's the twist. These behemoths, despite their grandeur, actually destroy the active star-forming regions they were born in by evaporating the surrounding gas away.
So they sort of seal their own doom?
In a sense, yes. While the most massive stars wind up being the brightest, most luminous, and most easy to see, they're also the fewest in number.
The irony of the cosmos.
Indeed. And here's more irony. While a large star-forming nebula might form tens or even hundreds of high-mass stars, it's going to form hundreds of low-mass stars for each high-mass star that forms. So while the brightest, hottest, bluest stars get all of the attention early on, they're mere flashes in the pan on cosmic scales. After only a few million years pass by, they'll all be gone.
So the saying, "the flame that burns twice as bright burns only half as long," really applies here.
Indeed, but for stars, it's even more extreme. It's a fascinating, if somewhat tragic, cosmic dance. It gets even more dramatic, you know. A star that's twice as massive as another burns through its fuel about 8 times as quickly. And a star that's 10 times as massive, it will live less than 1% as long as the lower mass star. Compare this to a star like our sun, which might last for 10 to 12 billion years.
That's a lifetime in cosmic terms.
Absolutely. But a star that's tens or even hundreds of times as massive as our sun will reach the end of its life after only a few million years have gone by, at most. And unlike the sun, which will die gently in a planetary nebula, the most massive stars will die in violent stellar cataclysms, such as core collapse supernovae.
It's like a cosmic fireworks show.
Exactly. Early on in the star-forming episode that gave rise to our solar system, the protostar that would become our sun was still pulling in matter, growing and working to collapse down to form a central star orbited by a disk of matter. This is from where planets and more would eventually arise.
Meanwhile, the heavyweights were burning out.
Yes, the most massive stars around it furiously burned through their fuel, exploding in supernovae events, putting an end to star formation in any surrounding environments where they successfully evaporated all of the gas away. The universe is a violent place, and star-forming regions are some of the most violent places of all. A mix of birth and death on mind-boggling scales.
So where does our sun fit into all of this?
When we look at our sun in comparison to all the other stars that form in the universe, we're a far cry from the most massive ones of all. However, when we compare our sun to the low-mass end of the stars we find, we learn we aren't exactly among the least massive stars either. It's all about perspective. Our sun started out larger earlier and grew faster than the vast majority of clumps that are present. Today, it's more massive than 95% of all the stars that are out there.
So we're kind of a big deal in the universe then?
In a way, yes. In fact, somewhere between 75 and 80% of all stars are red dwarf stars, the lowest mass, coolest, and smallest class of star out there.
And where do we compare to these red dwarf stars?
Great question. Red dwarfs have no more than around 40% of the sun's mass. More than half of the rest of the stars are the next class up, K-class, which is still smaller, less massive, and cooler than our sun, from about 40 to 80% the sun's mass.
So we're actually quite unique.
Indeed, we were above average in terms of mass, but we were typical in one very important fashion. We were alone, without any other stellar companions in our system.
That's quite a solo journey.
Indeed it is. In most of the large star-forming regions we find in Milky Way-sized galaxies, thousands of new stars are born. Of these, many of them will be bound together in multi-star systems, but about half of them will be single stars without another stellar companion.
Quite a celestial dance, isn't it?
A celestial dance indeed. A beautiful, deadly, and surprising dance. In the grand scheme of the universe, we've indeed carved out a unique spot for ourselves. We've long wondered why our sun is a single-star system rather than a multi-star system. It seems like it could have been born in almost any configuration.
So why did we arise in this specific configuration?
It might seem like pure chance, but we've discovered more than 5,000 exoplanets. And rocky planets that exist in what we call the habitable zone around their stars are practically non-existent in multi-star systems.
So we're a single-star system because it's more conducive to life?
That's one way to look at it. Singlet star systems are the most likely to house potentially habitable worlds, something we absolutely required if we were going to arise within this universe.
That's incredible. So how did our sun form in the first place?
The fragment of the gas cloud that turned into our sun accrued matter onto a central clump, forming a protostar. This protostar radiated heat away, allowing it to collapse and become denser.
And that's when the magic happens?
Exactly. The temperature in the innermost central core of this clump started to rise due to gravitational collapse. At some point, a critical threshold is reached, a temperature of 4 million K, which is the point at which protons can begin to fuse into heavier elements through the process of nuclear fusion. This marks the moment that our star, the sun, is officially considered to have been born.
And when was that?
To the best of our knowledge, this moment happened 4.56 billion years ago, when the universe was approximately 2/3 of its current age. The central star ignites, and that triggers a violent set of downstream effects.
It's amazing to think about how our sun was born and all the processes that went into it.
It certainly gives you a different perspective on the sky, doesn't it? This really is a remarkable story we're finally able to tell, all thanks to the power of modern observatories like the Hubble, ALMA, the VLT, and JWST. They've allowed us to observe stellar systems in their very early stages of formation. We've spotted central stars and protostars shrouded by gas, dust, and often protoplanetary disks with gaps in them.
Sort of like witnessing the birth of a star system.
Precisely. These gaps are the seeds of what will become giant and rocky planets, leading to full-on stellar and planetary systems like our own.
So where do we fit in all of this?
Well, most of the stars that form, including very likely our own, were born amidst thousands of others in massive star clusters. However, these clusters rarely persist for long. Nearly all clusters end up ejecting their members and dissociating completely in under 1 billion years.
So we're like cosmic orphans in a way?
In a sense, yes. The history of the universe may have separated us from our stellar and planetary siblings, scattering them across the galaxy, but our shared history remains.
It's almost poetic, isn't it?
It certainly is. Whenever we find a star with approximately the same age and abundance of heavy elements as our sun, we cannot help but wonder, is this one of our long-lost siblings? There are likely thousands of them roaming the galaxy. Perhaps someday, we may be able to identify our cosmic brothers and sisters that grew up in the same nursery that we did all those billions of years ago. And there you have it, folks. We've journeyed through the cosmos today, understanding the birth of our very own star, the sun, and the intricate processes that led to our existence. From the elemental needs for life's birth to the solitary nature of our star system, we've unveiled the cosmic mystery of our solar family's origin. It's like we've been playing a giant game of hide-and-seek with our celestial siblings.
Absolutely. And even though the universe scattered us apart, our shared history remains and continues to intrigue us. Who knows, we might someday find our long-lost cosmic siblings roaming the galaxy just like us.
In this vast universe, we're simply stardust with questions, and every answer we find only leads to more mysteries. It's a game that keeps on giving.
And speaking of giving, if you enjoyed today's ride through the cosmos, please blast that like button, leave us a comment, and share this episode with your friends. Let's spread the cosmic curiosity.
Absolutely. Thank you so much for tuning into Curiosity Wonderland today. We appreciate your support and your insatiable curiosity. Until next time, keep looking up.
Goodbye, everyone, and keep exploring those stars.
I discovered this fascinating story on the Big Think site in an article titled, "What Was It Like When the Sun Was Born?" written by Ethan Siegel and published on February 1st, 2024. The full URL is in the video description if you want to delve deeper into the subject. All right? Now, I'm off.